This video discusses scatter plots, which is a way of displaying the relationship between two numerical variables, and correlation coefficients, which is a way of quantifying that linear relationship. So first of all, scatter plots. Scatter plots are useful for seeing how two variables covary. All the observations are displayed on the plot, and the position of each depends on its value on each of the two variables. By convention, we typically put the exposure on the x-axis and the outcome on the y-axis, hence why these are sometimes called x and y variables. If we look at this fictitious plot here, we can first of all ask, is there a relationship? And clearly there is. As x increases, y also increases. So the direction of the relationship is positive. We can also have a negative relationship. In this case, as x increases, y tends to decrease. Likewise, we may also have no relationship at all. In this case, y has a constant value for all values of x. The scatter plot also gives us an indication of the strength of the relationship. If there's little variation around the underlying pattern, then the relationship is said to be strong. In practice, this would mean that if you had observed a value for x, you can make a pretty good guess as to what y would be. Likewise, for scatters that vary a lot around the underlying pattern, the relationship is clearly weaker. So while we get a good guess of what y is by knowing what x is, there's still a lot of variation around y. Scatter plots are an important part of any analysis because they allow us to assess the form or the shape of a relationship with one another. This form needs to be correctly specified in any subsequent statistical analysis, as you'll see in a minute in the discussion of correlation coefficients, and also in the section on regression modelling. An incorrect specification or a failure to understand the functional form of a relationship can lead to errors in conclusions. The shape of a relationship is sometimes summarised by the mathematical function that best describes it. These scatter plots show examples of a linear relationship, a quadratic relationship, and an exponential relationship. So here's a real example looking at the relationship between maternal body mass index, BMI, and offspring birth weight. So the scatter plot suggests that on average, babies born to mothers with a higher body mass index tend to have a higher birth weight, i.e. there's a positive relationship. The relationship is fairly weak in individual terms in the sense that knowing a mother's body mass index tells you little about the birth weight of their child. However, it's worth saying that just because this relationship is weak, it does not mean that it's unimportant. As we'll discuss more in later videos, if the relationship is causal, then shifting the entire distribution of maternal BMI up by only 1 kilogram per metre squared might have important public health implications with respect to the entire population, because it will shift the whole distribution of birth weight up, which is a lot of people. This sort of interpretation requires some contextual understanding. For example, in this case, we would need to know the implications of a higher birth weight on later health. However, the point is to say that we cannot draw implications from a graph using statistical information alone. In this case, the statistical information was the strength of the relationship, and that we often also need subject matter knowledge. Scatter plots can also be extended to summarise data in more than 2 dimensions through the use of colour and size of the markers. This is an example from the Gapminder project. Their website is worth a look because some of the examples demonstrate how plots can provide illumination and insight to complex data, and most of their applications are to do with global health. So this plot shows a fairly strong relationship between health and wealth across different countries. Extra dimensions have been added through the colour of the markers, which relate to different geographic regions, and the size of the markers, which relate to the size of the country. So we're now going to talk about the correlation coefficient, often just abbreviated to R. So the correlation coefficient is a sample statistic used to quantify the strength of the linear relationship between two variables. It can take values from 1 to -1. 1 is a perfect positive correlation, -1 is a perfect negative correlation, and 0 indicates no linear relationship or no correlation. So if we get values close to 0, then we may also say that the two variables appear independent of each other. And we'll develop our ideas of independence in sections on statistical inference and probability. The calculation of the correlation coefficient is based on standard deviation scores, which means that each observation is expressed in terms of its deviation from the mean in units of standard deviation. The video on transformation explains this in more detail. But what this means is that R is a unitless measure. For example, if we looked at the correlation between birth weight and birth length, we would get exactly the same correlation coefficient regardless of whether we use grams or kilograms or centimetres or metres as our measurement units. Now if you pause to think about this, it will hopefully follow that the correlation coefficient tells us nothing about the steepness of the slope of the line in a scatter plot, or how much y changes with respect to a unit change in x. But what it does inform us about is the degree of scatter around a linear line, or the shape of the ellipse. So as the scatter gets bigger, or the ellipse gets fatter around the line, the correlation coefficient tends to 0. So in these three plots, the line has the same slope, but the scatter around it is wider, and hence the correlation is weaker. So hopefully that gives an insight into why the correlation coefficient is a measure of the strength of the linear association. One last thing to reinforce is that it quantifies the linear aspect of the relationship. So if the relationship is not linear, then a correlation coefficient of 0 does not imply that there is no relationship at all, just that there is no linear relationship. And this is highlighted in this figure here, which shows a correlation coefficient of 0 for a quadratic relationship. So correlation coefficient should only be used when the shape of the relationship is linear. To use them when the shape is nonlinear can mislead. Lastly, here is a list of terms introduced in this video.